Now that we're familiar with differentiation, you may be wondering if there are any practical applications for this operation. Well, there are. Derivatives of a function describe the slope of the graph, the change in y in relation to the change in x. So the derivative can also be thought of as describing the rate of change of the graph. One way you can use derivatives is when you have related rates. When two rates of change are related to each other, such as x and y, they basically describe how fast one thing changes in relation to something else. We actually already know many examples of related rates. Recall the equation to find the area of a circle. A equals pi r squared. The area is dependent on the radius, so the two values are related. They are not necessarily proportional to each other, but we can relate them in an equation. If we take the derivative of both sides, we can see that the rate of change of the area and the rate of change of the radius are also related. Let's take a look at how this works. So Pablo is getting ready for a party and he needs some help. He wants a new table for the party, so he hires a carpenter. Imagine that we're the carpenter and we're thinking of building a tree slice table, kind of like that. So you plant a tree and you want to know how fast the cross-sectional area of the tree trunk is growing. If the tree grows a new ring around its trunk every year with a radius of 0.5 centimeters, how fast is the tree trunk's cross-sectional area growing after, say, 6 years? Now let's step inside and set up our equation.
We've got a picture and we know what's going on. We know that the tree is expanding in area and it looks like roughly the size of the shape of a circle, so we can go ahead and approximate that with A is equal to pi r squared. That is the area of the tree stump. And now we want to know how fast the area is growing, so the rate of change of the area. So we can just take the derivative of both sides. dA over dt in terms of time is equal to, well, we do implicit differentiation, 2 pi r times dr over dt. We have to remember the dr over dt because we are differentiating this in regards to time. Now, we know dr over dt, that is 0.5, but can we figure out r? Yeah, we can. We are given that dr over dt, which is how fast the radius is changing, is 0.5 centimeters per year, and we know how many years it is. So we multiply that by 6 years, and we get 3. So we know that r is equal to 3 in this instance, and this is assuming that the tree radius starts at 0. So dA over dt is equal to 2 pi times 3 times dr over dt is 0.5. So the 2 and the 0.5 cancel out. We're left with dA over dt is equal to 3 pi. And don't forget units. We are in centimeters squared per year. Now we know that tree grows by 3 pi centimeters squared per year. That would make for a very long wait if you want to make a table from scratch.
Great, I've got a table now. But now I have another problem. My cat climbed up the tree and won't get down. Time for another related rates problem. So this is a step up though. We know that related rates work with area. But do they work with distance? I'm standing roughly 9 meters away from the tree, and the cat has climbed, I'd say, a 16-meter tall tree. He's now making his way down from the top of the tree at 4 meters per minute. How fast is my cat coming towards me after 1 minute? Or in other words, how fast is the distance between me and the cat shrinking after 1 minute? Let's work it out.
Our next problem looks a little bit more daunting than the last one, but let's see if we can model it in a way that we know how to solve. So if I'm 9 meters away from the tree and the cat is 16 meters up, that means, hey, this looks like a triangle. right triangle at that, so we can use Pythagorean theorem to solve this. So Pythagorean theorem is a squared plus b squared is equal to c squared, which is the hypotenuse. And we want to find out how fast the cat is coming towards me. So how fast the hypotenuse is shrinking. And let's take the derivative of everything. We know that, let's call the height of the tree b and the distance between me and the tree a. Well, we know that a is constant throughout this problem, but b is changing because the cat is coming down the tree. So if we take the derivative of both sides, a squared would not matter. We just do 2b db over dt is equal to 2c db over dt, because a would just be a constant. Okay, we can cancel out the 2's, but now we have to figure out what b is. We know dB over dt is 4 meters per minute. And we want to know how high the cat is off the ground after 1 minute. Well, we can just do multiplication. 16 minus 1 times 4. So the speed times the time, that's the distance, and 16 minus the distance that the cat has gone during that time, that is 12. So now we can substitute everything. We know b is 12, dB over dt, we're given that that is negative 4, is equal to c. And c we can find out because if b is 12 and a is 9, we use Pythagorean theorem. At that moment, the c would be 15. This is a 3, 4, 5 triangle. 15 dB over dt. Now it's really easy to solve. 12 times negative 4, that is negative 48. And both sides divide by 15. We get that is equal to dB over dt. And negative 48 over 15 we can simplify, or we not even simplify, just 3.2. And don't forget units. This is in meters per minute. That is how fast the cat is coming towards me. That's a very slow cat.
Okay, now that we've got that sorted, I was thinking of surprising Pablo with some decor for the party. Let's take our knowledge on related rates three-dimensional. I think some balloons would make a great addition to the ambience of the party. If I can blow into the balloon at a steady rate of pi centimeters cubed per decasecond, what rate is its radius increasing after 36 decaseconds? I'll have to make some assumptions to solve this problem. First, we'll assume that the balloon is spherical, which makes it a lot easier to solve.
Our third problem, we have a sphere. Okay, well, 3 dimensions seems quite difficult, but we actually know how to find the volume of a sphere. The volume of sphere is 4 over 3 pi r cubed. Well, we want to know how fast the radius is increasing. We know how fast the volume is increasing. So let's take the derivative of both sides to find the rates of change. dV over dt is equal to, that would be 4 pi r squared times dr over dt. Okay. Well, we know dV over dt. 4 pi is a constant. And r squared, can we figure out r? Well, we know that it's been 36 deciseconds. And the volume increases by pi centimeters cubed per deciliter. So if we multiply 36 times pi, we'll get how many centimeters cubed the volume is after 36 deciseconds. So that is 36 pi centimeters cubed. And we have our volume equation. So 36 pi is equal to 4 over 3 pi r cubed. Now it's really easy. We can cancel out the pi's and then do a little bit of rearranging. 36 divided by 4 is 9 times 3 is 27. So 27 is equal to r cubed. Now take the cube root of both sides and we get r is equal to 3. So now we have dv over dt, that is pi, is equal to 4 pi, 3 squared is r squared, and we want to figure out dr over dt. So we have everything we need. Pi's cancel out, we move the 4 to the other side, that's 1/4, and we move the 3 squared to the other side, that's 1 over 4 times 3 squared is 4 times 9, which is 36. So 136 is equal to dr over dt. So after 36 deciseconds, the radius of the balloon is increasing by 1/36 of a centimeter cubed per decisecond.
We'll need drinks at Pablo's party as well. He started filling up this cone, but gave it to me to pay for. I'm filling up a conical flask with a height of 30 centimeters and a diameter of 20 centimeters. I don't know which price drink Pablo selected to fill it with, but I want to make sure I'm getting my money's worth. This dispenser is really high-tech and changes its rate of dispensing to make sure that the height of the water line increases at a constant rate. So when the height of the water line in the flask is 3 centimeters high, it is going up at a rate of 1 centimeter per second. And I see the dispenser telling me that I'm paying 0.95 cents per second. How much does the drink cost in cents per liter?
Our last question is a little bit harder than the other one, so we're going to do it on a piece of paper. Let's start by drawing our conical flask. This helps us visualize a bit. So it's a cone, and we know the height is 30 centimeters. We know the diameter is 20 centimeters, so the radius must be 10 centimeters. Now we want to know how much each volume of this liquid costs. So we might want to start with finding out the rate of change of the volume first. And to do that, we can use the volume equation of a cone, which we know is 1/3 pi r squared h. Now we can't take the derivative right away because we have 3 variables here. We have v, we have r, and we have h, and that is too complicated. So what do? Well, we know we are taking the rate right at 3 centimeters. That's 1/10 of the height. Well, it looks like it's a similar triangle, the small one and the big one, and it is. So the radius is indeed 1 centimeter. So the radius is just 1/3 the height, always, throughout the entire height of the cone. Let's just substitute that right away. V equals 1/3 pi h over 3 squared h, and that is equal to, well, we have 1/3 pi, that's h cubed over 9, v is equal to pi h cubed over 27. Now we can take the derivative of both sides because we only have 2 variables. dv over dt, that is what we're trying to solve for. Pi over 27, that is our coefficient, so we leave that. H cubed, what is the derivative of that? That is 3h squared.
I didn't put dh over dt because it's just equal to 1, so it cancels out.
Now, we need to know h. And we are given that. We're given that is 3 when the height of the water line is 3. So dv over dt is equal to pi over 27 3 times 3 squared. 3 times 3 squared, that is 27. So that cancels out. dv over dt is pi. And this is in centimeters cubed per second. And a centimeter cubed is the same thing as a milliliter. And since the question asks for liters, this will be easier to convert if we are having it in milliliters. Okay, now we have to connect those to the price, but how do we do that? Well, we're given that the price is 0.95 cents per second. That's just about 1 cent per second. And we're given that, well, we calculated that we're getting pi milliliters per second. So we're getting pi milliliters per second and we're paying 0.9 cents per second. So that means we're paying 0.95 cents for pi milliliters every second. 0.95 cents per second. So that's just about 1 cent per second. And we're given that, well, we calculated that we're getting pi milliliters per second. So we're getting pi milliliters per second and we're paying 0.9 cents per second. So that means we're paying 0.95 cents for pi milliliters every second. So that is actually just a ratio. So we want to know the cents per liter. So we can put cents on top, the volume on the bottom, and we can use a bit of dimensional analysis to find out what this answer is in liters. So we know 1000 milliliters in 1 liter. So this is just equal to 1, so that's why I can multiply it like that. And, well, we get
950 over pi
cents per liter. And that is about approximately 302 cents. But we'll keep our answer as an exact answer. But just for experimental reasons, 302 cents per liter, that's about $3 per liter. So this substance, this liquid, is probably either juice or pop. Now I know Pablo's tastes.
Thanks to calculus, the party will go off with a bang. Implicit differentiation really does have applications. Now you know how to use related rates to solve problems.